Hi, my name is Tyler Fees, and today I'm gonna give a presentation on the effects of lift and drag. Here we got the lift equation. These are all the factors affecting lift. I know it looks complicated when you first look at it, but once we break it down and take each portion step by step, it becomes pretty easy and understandable. There's a few things on here that you'll find out that the pilot can affect, and there's a couple things on the equation that the pilot doesn't have any control over. But first I'd like to go over a couple key terms before you start dissecting the lift equation. First term is airfoil. Okay, an airfoil is any surface, for example a rotor blade, that has aerodynamic forces, creates aerodynamic forces when a stream of air flows over it. In this case, this drawing that I have here is a cross-section of an airfoil, and I'm using an airfoil out of a Robinson 22, which is a symmetrical airfoil. Symmetrical airfoil, the curvature is the same from the top to the bottom. And if you're wondering what this line I drew to the center of it is, it's known as the chord line. The second term I'd like to go over is relative wind. So we got relative wind. Now relative wind is created by the motion of airflow through the air. So an example is the air felt by the airfoil. It acts parallel and opposite to the flight path of the airfoil. So the wind felt by the airflow is known as the relative wind. So if a rotor blade system was just sitting on the ramp and the wind was blowing and air's flowing over it, that air flowing over is known as the relative wind. And it acts on the airfoil and creates lift just sitting there. So you can imagine when the RPMs are up in the green that you have a lot of relative wind being felt by the airfoil. So next, I'd like to go over angle of attack. So I use the acronym here, AOA, for angle of attack. Now angle of attack is the angle between the chord line, and this arrow here is referencing the relative wind. So the angle between the chord line and the relative wind is known as the angle of attack. So talking about the angle of attack, we can just throw up here as well the pitch angle. Now the pitch angle is the angle of the pitch in reference to the rotor hub. For example, the collective, when you pull the collective up, you increase the pitch of the rotor blades or increase the pitch angle. Now by doing that, by increasing the pitch angle, you're increasing the angle of attack by the chord line and the relative wind, because the angle of the blade is going to increase, and that relative wind felt by the rotor blade is going to increase, and you're going to have a higher angle of attack. Now with the higher angle of attack, you have more lift, and the byproduct of lift is drag. So we got our drag. That's another key term today. It is the force that resists the movement of the helicopter through the air produced when lift is developed. So the more lift you create, the more drag you're going to create. So now that we got some key terms on the board here, we can start dissecting our lift equation. And first, L here stands for lift. Obviously we're going to get to the lift after we go through these. Coefficient of lift. Coefficient of lift is the airfoil shape. In this case, like talked about, is symmetrical, and the angle of attack. So the pilot can affect this area of the lift equation by increasing the pitch angle, higher angle of attack, more lift, and more drag as well. So this half rho is the density of the air. Pilot can't control the density of the air. but it's affected the lift. For example, if you're at sea level, the density of the air is a given. When you go higher up, the air is less dense and thinner, you make less lift. This is a big one here. This is velocity squared. Now squared, it's a big portion of this lift equation. For example, if you double the airspeed, the result of that is it's going to create 4 times more lift. So the velocity of the air, the relative wind felt on the rotor blade is a big portion of the lift equation. That's why it's so important to keep our rotor RPMs up to make the required lift for flight. So lastly, we got our surface area. Surface area is basically just the area of the rotor blades. The pilot can't affect this portion of it. However, if you had bigger rotor blades, you would be creating more lift. So that, in a nutshell, is the lift equation. Just to review a little bit, the coefficient of lift is the shape of the airfoil and the angle of attack, and the pilot can control that. Half rho is the density of the air, the velocity of the relative wind, or the velocity of the rotor blades, or your RPMs, or in fixed wing, you know, the airspeed. And the surface area of the rotor blades. And if you times all this together, you come up with how much lift you're creating. And once again, the velocity is primarily the most important aspect of this lift equation. And blade twist, I just wanted to touch real quick on blade twist before I conclude. The blade twist is the R22 has a blade twist of -8, and what that means is for a given rotor RPM, the tip of the blades are the velocity at the tip of the blades is much faster than the velocity in the inner portion near the rotor hub. So the blades are twisted in a way that they have a higher pitch angle toward the middle of the blade, or toward the inside of the blades, to compensate for the speed difference in the rotor blade. And that just kind of goes in with the velocity of the rotor blades there. So with that, I'm going to conclude. And I hope you learned something. I hope you understand how the lift equation works and how it's broken down, and you'll be tested on it. Thank you.